All right, let's talk about Apache Kafka. If you're a developer and you've got a system design interview coming up, this is for you. We're going to skip all the dense jargon and really build up the core ideas you need to sound like you know exactly what you're talking about.
So, to really get Kafka, we're not going to start with Kafka itself. Nope. We're going to start with a problem, a classic engineering nightmare that every big tech company runs into. How on earth do you handle a massive, real-time flood of data without everything just falling over?
So picture this. You are building the real-time update website for the World Cup. We're talking millions of concurrent users. Every single goal, every yellow card, every substitution needs to show up instantly. And, crucially, the events for each soccer match have to appear in the right order. Sounds simple, right?
Your first attempt, your version 1, probably looks a little something like this. You've got a producer, some server sending events, sticking them into a single queue. And then you've got a consumer on the other side pulling them out to update the website. And you know what? For a small-time game with a few hundred people watching, this works just fine.
But this isn't a small-time game. This is the World Cup final. Suddenly, you've got millions of users, and events are just pouring in. Your single consumer is, well, it's getting completely crushed. It just can't keep up. The website starts to lag, and you're showing goals a minute after they actually happened. It's a disaster.
So you think, okay, easy fix. I'll just add more consumers to share the load. But look what happens. A goal for one team might go to consumer A, but a substitution that happened after that goal gets sent to consumer B. If consumer B is just a little bit faster, the substitution shows up on the website before the goal. The order is totally scrambled, and your real-time app is now worse than useless. And this is the exact problem that Kafka was built to solve. It has one core brilliant idea that fixes both the scaling problem and the ordering problem in one elegant move. And that idea is called partitioning.
Here's the secret sauce. Kafka uses a key. In our case, we'd use the match ID to decide where messages go. The rule is simple. Every single event from the Brazil versus Argentina match is absolutely guaranteed to land in the exact same processing lane, the same partition. That's it. That's how you guarantee that for any given match, the order is always perfect.
And this just shows the difference so clearly. Before, we had a single file line, total chaos, where one slow person holds everyone up. With Kafka, we've built a multi-lane superhighway. Each lane is dedicated to a specific match, so it flows smoothly and in perfect order, while other matches are being processed in parallel in the lanes next to it. You get scale and you get order. It's brilliant.
Okay, now that we have that main idea locked in, let's build out our vocabulary. Getting these core terms right is absolutely key for sounding sharp in any design discussion.
First up is a topic. Honestly, just think of this as a name, a label for a category of events. In our case, football events would be the topic. It's really just a logical container for our data stream. Super simple.
All right, now for the partition. This is the real workhorse of Kafka. It's basically just the log file on a server where data gets written in order. This is the true unit of parallelism, and this is the boundary where order is strictly 100% guaranteed. Our one topic is made up of many of these partitions.
In a broker? Even easier. A broker is just a server. It's one of the machines in your Kafka cluster. That's all it is. These brokers are the computers that actually host all those partitions we just talked about.
And finally, the consumer group. This is how we get that parallelism on the reading side. You just spin up a bunch of consumers and put them in the same group. Kafka takes care of the rest, automatically making sure that each partition is read by exactly one consumer from that group. And hey, if one of your consumers dies, Kafka just reassigns its partition to another one. Bam! You get fault tolerance for free.
Okay, so we've got the vocabulary in our back pocket. Now let's follow a single goal-scored event through the whole system, from the moment it's created to the moment it's processed.
So, it starts with the producer. It creates a message with that critical match ID key. Kafka does a quick bit of math, a hash, on that key, and that tells it exactly which partition to send the message to. The message gets written to that partition's log and is given a permanent number called an offset. Later, a consumer pulls that message, processes it, and then tells Kafka, hey, I'm done with everything up to offset number 123. That's called committing the offset, and it's basically the consumer's bookmark.
All right, now for the part that really matters in an interview. Knowing the components is one thing, but showing you understand the trade-offs, that's what demonstrates real engineering thinking.
The absolute classic Kafka trade-off is durability versus latency. See, when a producer sends a message, you can tell it how long to wait for a confirmation, or an ACK. If you set ACKs to all, you're telling the producer, don't you dare move on until you know for sure this message has been safely copied to multiple servers. This gives you the strongest possible guarantee you won't lose data. But of course, it's also the slowest option. It's a fundamental trade-off.
So let's boil it all down. Here is your interview-ready mental model. If you can explain these 4 points, you're golden. Number 1, partitioning is Kafka's magic trick for getting both scale and order. Number 2, consumer groups are how you read in parallel and make your system resilient to failure. 3, offsets are just bookmarks for consumers. And 4, replication is how you make sure data is safe, but it comes at the cost of higher latency.
And that leaves us with one last really critical question to think about. We've established that the partition key is the foundation of this whole system. Everything relies on it. So what happens if you pick a bad one? What if one match is generating way more events than all the others combined? That's the hot partition problem. And thinking about how to handle that is what separates a pretty good system design from a truly great one.